So I would like to go through a phase of analysis in Scandinavia during the previous century, where I think that Scandinavian mathematicians really played a very central role. And I'm going to do it, so to say, from scratch, from the beginning. So I apologize to experts because this will be in most part very elementary. So the part that I would like to talk about is geometric function theory. And the contributions of the Scandinavian mathematicians here have been very decisive. Actually, there have been two different schools somehow competing during the previous century. It was the Scandinavian more geometric school, and it was a school of singular integrals which emanated basically from Chicago. This part which I'm going to talk about has been very influential on my own work, but on the other hand, the selection of topics will therefore, the selection of topics will therefore be very personal. I'm not making any kind of effort to describe the development of mathematics in Scandinavia, not even of analysis in Scandinavia. So it's, in any case, very natural to start with Abel. Not really because his work is very close to what I'm going to describe, but rather because he meant so much for the general development of mathematics in the beginning of the 19th century. If you read work by, say, Courbet or Cauchy, you find yourself in a work which is very different from our own. So for them, mathematics seemed to be like a formal game, and it was somehow free and in an unclear way coupled to what happened in nature. Abel, Dirichlet, or Riemann, however, they seem very modern if you try to read them. So let me, as an example, mention the 1837 paper by Dirichlet, where he proves the convergence of Fourier series for piecewise smooth functions. And it could be compared to what, for example, Cauchy tried, where he based his idea on a partial integration of the coefficients, and then they behave like 1 over n, and then he compared that series to the series sine n over x over n, which one u converges. So therefore he compared two non-absolutely convergent Fourier series to each other, which we teach in our first classes, I hope, is not really allowed. And Dirichlet objected to this, and he even gave a counterexample that you cannot argue like that in his 1837 paper. And just to show how modern Dirichlet was, he mentioned that if you take the function which is 0 for rational values and 1 for irrational values, how do you define the coefficients? Which seems at 1837 to be an amazing statement if you compare it to the very formal mathematics of the earlier people. So in this way, one can say that this was the beginning, as I see it's the beginning of the distinction between, so to say, pure and applied mathematics, or pure, where it was one singled out pure mathematics where you really required to have definitions and you required to have proofs, and you didn't allow infinity in a formal way. I happened to see recently in the monthly bulletin from the French Academy the following quotation from a letter from 1830 from Jacobi, who belonged then to the new generation of mathematicians. A letter from him to Legendre, and I have written it down to make this work. Does this work? No. So how do I do now? So someone tell me how you adjust this. It's okay. Maybe my side. Okay, thank you. So maybe I should read this. Fourier has the opinion that the main purpose of mathematics is the explanation of natural phenomena. Being a philosopher, he ought to know that the only purpose of science is the glory, it's called honneur in French, of the human mind. And for this reason, a question in number theory has the same significance as a question concerning the structure of the world. And I think one could look at this as the credo of pure mathematics. So complex analysis during the 19th century was and in the early part of the 20th century was dominated by the Cauchy-Weierstrass French school power series approach. So Riemann's much more geometric approach became important only when one had a serious and rigorous treatment of the Dirichlet problem for harmonic functions. And this was what was realized by Scandinavian mathematicians. And the first who really made a significant contribution here, and a very significant one, was Jensen, whose proof in 1819 came in 1899. And I want to give the full title of this paper, which is one of the fundamental papers in analysis, aspiring to its simplicity. So the title is A New and Important Theorem in the Theory of Functions. And I think that was really an understatement. So let me remind you of what it means. So I've written down the statement there where the value of the logarithm of an analytic function in the unit disk is obtained from its boundary values and the zeros of the function and the poles of the function. So this is for a meromorphic function in the unit disk. And there are two particular consequences of that, which I think is actually completely fundamental for all, well, the most essential part of the early complex analysis in the beginning of the 1900s. Namely the statement, the first statement that the logarithm is not the function is not too small, which is described there, and that there are not too many zeros in a very precise way. And that, you know, both these statements are sharp. And much of what I'm going to say will be different illustrations of this. So that was the first very important paper that goes back to the Scandinavian mathematicians. And the second was a contribution by the Finnish mathematician Ernst Lindelöf. And that was in the 1910s. He had several papers. And the statement can be given like this. One of the most important versions is given here. So it's related to what happens on the boundary for an analytic function. If it has boundary values along one curve, so if it is bounded and if it converges along one curve, which is called gamma there, to a certain limit, then it converges to the same limit uniformly in an angle. So that means in particular that if there are two limits coming from along different curves, they have to be the same, because they both would produce the limit you get from the center. And the proof of this is even more important than the statement. Namely, you get in this way the what you call the principle of the harmonic major. And this is where the solution of the Dirichlet problem starts to interact with complex analysis. So the principle of the harmonic, this is how you prove that. You use the statement below, namely that if you majorize the logarithm of an analytic function on the boundary by a harmonic function, you get the same bound inside also. So the special case is if you have a bound on one piece of the boundary, which I call 1 here, and another on another part of the boundary, you can get a connection how big the function can be at inside points. And this sounds very innocent, but this also has a tremendous influence on the development of analysis last century. So before I proceed, I would like to go back to the Jensen formula and tell you about the Nevanlina theory, because then we will be lost in technicalities here. So let's go back to Jensen's formula here. And you apply Jensen's formula to the function f minus a constant. And if you apply it to the function which is given by the values on the circle of radius r, you obtain a statement like the one I've written down there, where you get an estimate of two different things at how they balance each other. One is how close the function is to the value a, and the second is how many times it takes these values. And what happens is that there is a complete balance between these two, so when the point varies, the sum of them is constant. That's the constant of Jensen's formula. And that common value is called the characteristic function of the function f. So I wanted to mention this because this was Rolf Nevanlina's great contribution to mathematics, and I will have no reason to come back to it, and I thought it would be wrong somehow not to emphasize this on the way. So in particular, if you take a function in the unit disk, you get a statement that this function T of R, the characteristic function, is bounded. That's the same as saying that the function is a quotient of two bounded analytic functions. And this has a certain relation to my own work, because my thesis, which nobody remembers anymore, was dealing precisely with the subclass of these functions, where you assume more regularity on the function than being bounded. So the most important aspect of what Nevanlina did is what you have written further down here, namely that you can bound any sum of a finite number of these functions, n, by twice the characteristic function if you allow a small remainder. And if you think about it for a moment, you realize that this contains the Picard theorem, which was a great theorem at the turn of the century. That was a very influential and was considered, I suppose, one of Picard's really greatest achievements. And this is generalized in a very fundamental way by Rolf Nevanlina. And this, of course, is much harder to prove than the Jensen formula. Okay, so this was the tribute to Rolf Lennart. So let me go back to the issue before, where we were estimating, trying to balance a function from its boundary values. So this is, we are now about 1930, and D'Anjou had formulated a conjecture about entire function, which is called the D'Anjou conjecture, which deals with the number of asymptotic values of an entire function. And what that means is, I can explain it from this picture. So what this means is that you have a certain number of paths which go to infinity from the origin, say. And you have an entire function which converges to different values along different curves. And the question is, how many curves could you have, depending on how big the function became in between. And D'Anjou had the conjecture that if the function was of the order rho, you would have at most twice that number of paths with different asymptotic limits. And this is formulated in the first statement there. So the question is, why would it be, why is that about? I mean, why can't it go to any kind of limits? And the reason is precisely this statement that I gave about how Lindelöf explained how you cannot have different approaches for a boundary function. You cannot tend to different limits when you go to the same point, in a half-plane, for example. So what that means is that if you have two curves going to infinity, and you have one value, say 0, along one curve, and another value, like 1 along the other curve, the function cannot be bounded in between. So it has to have a certain growth. And that you can estimate precisely from that picture which I have drawn here. So you have values less than or equal to 0 on 1. But I probably made a mistake here. Anyway, it cannot be different along two different curves unless it is extremely big on the big circle which remains further out. And that means that the harmonic measure of the piece of the circle which is very far out cannot be too small, because it has to, you should compensate it by the factor r to the rho. And that gives precisely this statement about the harmonic measure, which I have written down, that you will see naught is less than r to the minus rho. And the question is, if the harmonic measure behaves like that. So you have an angle which goes out, and you have this circle way out, and you want to see how much harmonic measure that would have way down at the origin. And that depends on the angle. I mean, the larger you make the angle, the larger the harmonic measure of the piece outside. But you have to have a very precise estimate. And this is what Alfors did in his first paper on this subject, which was from 1929. So by analyzing the geometry here, which is not, these curves can be very complicated, so you need some kind of machinery to estimate that. And he made very clever use of conformal mappings to do this estimate. And this was one of the main reasons why he was given the first field medal in 1936, which was the first peace medal that was given. And then the very unlikely thing happened here that he was in Helsinki, but in Uppsala, in the other Scandinavian country, Berlin was sitting and writing his thesis and proving exactly the same theorem. But then the story goes that he didn't publish this because he wanted to, his father invited him to a crocodile hunt somewhere in South America, so he postponed the publication of his result. And when he came back, the authors had already published that. But then they became great friends and they worked out together what is now called the theory of extreme length, which I would like to describe to you because it has been so fundamental in function theory. So if one wants to make a guess about the real history here, the basic idea from Berlin in his teaching is that the idea of using a very general weight, which is part of the game today, comes certainly from alpha. So it's a very good balance, I think, of the ideas for most these people. So the idea is that you want to estimate the harmonic factor, which is 1 on the curve alpha and 0 on the rest of the boundary. And you want to estimate it at the point d0 somewhere. So you should think of alpha as being way out somewhere in a region where you don't know so much, while the geometry of the domain around d0 is irrelevant. So think of this as a long sector-like picture. So the idea is that one should study a general metric in this domain, and you should measure curves like gamma in terms of the metric rho, and you measure the area the way I have written A of rho there. And you look at the quotient, you scale away the area, and you get the number lambda of rho. And then you try to find the best possible rho here. You try to maximize the length, the shortest length as in relation to the area. And this is called extremal length. Now if you take a rectangle, it's easy to see that the best choice is rho identically 1. And that is just the fourth inequality for length, which is always behind the geometry. When you use geometry in analytic function theory, I mean, the length area comparison is always short inequality. So that is very easy to prove. I mean, anybody can do that. And the extremal length then is precisely B over A. But then you notice that if you take the harmonic measure of the curve alpha in this case, it's also a function of B over A, namely the one I wrote down there. It's just a conformal mapping of the rectangle to the circle gives you that, which is an explicit factor. And therefore you have B over A in both places. And the point is that both these notions are conformally invariant. I mean, the harmonic measure is obvious if you map a domain and the piece of the boundary to another. Of course, it's conformally invariant, the value at a given point. And the extremal length is also designed so that one of the metrics would be, if you have a conformal mapping, you can use the metric you get in one domain and transfer it to the metric in the other, just by multiplying by the derivative of the mapping. So therefore you have two conformally invariant things which are equal for the rectangle, but then they're always equal. And that means that the harmonic measure is always given in terms of the extremal length like that. And what makes this so wonderful is that if you pick any kind of metric now, you always get an inequality because the extremal length was defined by the soup. So by choosing any kind of metric, you get an estimate. And by being clever, you get a better estimate. So this is an extremely useful way of getting explicit estimates in terms of geometry. And for example, there was a famous inequality that Attractors had great problems to get in this conformal mapping approach, which you get here by just a particular choice of row. Okay, so this was one of the fundamental contributions of the combined Scandinavian mathematicians in the 1930s. Courant, who also was a prominent mathematician at this time, he also worked on this problem, and he had earlier obtained a slightly better, it's a worse estimate. I mean, we are estimating for the Darcy inequality where we are trying to obtain twice the order. But Courant had somewhat earlier found, I think, 5 laws or so, and using similar methods. So I would like to emphasize something that Courant had done, and most beautiful and perhaps most well-known is this theory of quasi-analytic functions. So maybe I can remind you of that. So I'm switching to something completely different now. Put harmonic measure behind you. So we are now dealing with the functions on an interval, and we are considering classes of functions which have a bound on the sides of the derivatives, the fourth line there. And the question was, if you know that the function has all its derivatives 0 at one point, when is it identically 0? Which would be the case if mn would be factorial n, because then the function would be analytic, and of course, if all derivatives are 0, the function is 0. And this was also a problem by Darcy, which Kahneman solved in a book which was published about 1925. And what I would just like to remind you is, with modern technology, so to say, how simple this is. So what we do is that we take this function, which is 0, has all derivatives 0 at the point, and define the function analytic in an upper half plane, which is called phi here in this picture. And then you get the bound on this, which is the formula under the definition of mu here. So what is not clear there is this function mu. And then we know that this function is analytic and not identical to 0, and therefore we use one of the Jensen observations, namely that the integral of the logarithm has to be greater than minus infinity. And if you transfer that to a half plane, you get the formula about log of phi. And then you have a bound from you have integrated, made a partial integration the way I have described there. And you have a bound on phi, and therefore the condition on mu, the log mu divided by 1 plus x squared has a divergent integral, implies that the corresponding integral for phi is minus infinity, and therefore the function is identically 0. And modulo certain technicalities, this is a complete description of Kahneman's book. You have to make a transfer, you have to check what the connection between this between this statement about the analytic function on the boundary and this statement about number, which is a statement about numbers there. So the factorial n case is the sum 1 over n here. But this also shows the power of Jensen's formula. I mean, without Jensen's formula, you would never think of doing something like this. So I cannot resist adding something where I would involve myself. Namely, this is a long time ago, and the Ehrenpreis Prize considered the same problem at the same time. Namely, you can replace the statement about the derivative being 0 at a point by asking which derivative can you prescribe. Yeah, you want to prescribe the derivatives at one point in terms of one sequence here, an, right? And you want to see, so if you prescribe the derivatives, how can you continue this function in this class C of n? And it turns out that this also has a very simple answer. So let me repeat this. You want to prescribe your derivatives at the point being less than a certain sequence of numbers. And the question is, can you continue it in the same class, or how much bigger do you have to make it? And the condition is precisely the one I have written down at the bottom of that line. So you see that the divergence of this integral here is precisely the quasi-analytic case. But if it isn't really quasi-analytic, you have a condition there on how big your prescriptions can be. So what is interesting is that, for example, if you take what is called the Junge class, where you increase the factorial n for analytic function by raising it to power, then these, so if you have the m meant to be the factorial n to the power of 1 plus alpha, say, then it turns out that this mu and this alpha are the same, which means that you can continue with the Frey function in the same class. But if you go down to the logarithmic approach of the analytic case, you cannot do that anymore. So if you try to prescribe something close to analytic, you cannot continue it in all quasi-analytic classes. So there are certain conditions to satisfy. And this again is harder, but not too hard, of course. So let's continue now and let's move to Hund. Maybe I do. So Marcin Ries was then the professor in Lund, and he is, of course, perhaps most famous for the inequality which I have written down on the top there, which connects the values of the real part of an analytic function to the values of the imaginary part of the analytic function. So that means that the integrals of the power p are about the same. So massively, so at this time there was a potential theory developed, as I said, that was done at the end of the 19th century, and if you should mention somebody there, it should be a Swede again. I mean, one could prove the solution of the Dirichlet problem using integral equations, right? And the Fredholm theory is a very important aspect of that. But we take that for granted, and what the if you have a bad boundary set, I mean, if you want to solve the Dirichlet problem for a very complicated curve or a complicated set, the only way to do this was to approximate the set by smoother cases and go to the limit, which is not too hard. This is what Taylor did, for example. And that was a very complete theory of potential theory at that time. But there was no theory no potential theory starting from scratch, so to say. And this is what Marcel Ries's student at that time, Frostman, did by using this integral, which is called the energy integral, and which goes back to Gauss area. So if you want to find the Green's function, for example, for a complicated domain, his approach was to study this functional, which I call I of mu here. And when I was preparing this lecture, it occurred to me that I have a copy of this thesis of Frostman from 1937, but it must be one of the most uncommon publications in the world. First of all, it was published in French, which may be okay, but also it was published in a journal which is almost secret. So there is was at that time a publication called the Communications from the Seminar of the Lund Mathematical Institute. And this was part of that. And while speaking of that, I want to emphasize that there is another paper in that same series which is also unavailable, so to say, and that is Seger's proof of the second term in the development of the Toeplitz determinant. It's a very beautiful paper, but they published the 50th anniversary or so, anyway, an anniversary of Marcel Ries in that series. So it occurred to me that maybe it would be a good idea to try to make a collection of these, not only these very difficult to find papers, but in general of papers which have been very significant and which are now incorporated in texts of for the courses in the university, to publish them as they were originally, so that people would start reading them. And when I was preparing this, I found what Bell write about Abel, because people kept asking Abel how it was possible for him in such a short time to learn so much about mathematics. And then his answer was that I was reading the original papers by the masters, and I didn't read their students. So I would propose some publisher to make a few volumes of old mathematical papers that would be collected somewhere, and then the paper by Frostman would suit them very well. I mean, it's extremely nice to read. So why do I mention that here? Well, because the extremal, when you solve this extremal problem, you get precisely the harmonic measure. So the density here of the extremal measure is precisely the harmonic measure of the set that we are considering at infinity. And this, of course, has the advantage that you can do it in any kind of dimension by changing the kernel. So a more recent topic in geometric function theory is the quasi-conformal mappings. So in the initial period, the Riemann mapping theorem was what is called the generalized Riemann mapping theorem, which is the solution of the Conformally equation, was proved by Arthurs and Beers. And later, it has been one of the main topics of mathematics in Finland. So the original theory was designed for the study of Riemann surfaces, and this is what is now very popular in any kind of form called the Teichmüller theory. And what Sullivan in particular has emphasized is how well this connects to dynamical systems. So this is, I would say, the main tool in the theory of dynamical systems. I had to be prepared, but maybe I pass over that. So, to finish this part, I would just like to say that this period of complex function theory, from the beginning of the century and up to, say, the 1940s or so, is what I would like to call the golden heroic period of the Scandinavian function theory. And the main actors here are in alphabetic order: Alfors, Berling, Kalman, Mellandina, and Ries. The interesting thing in this connection now is what they didn't do. There are two very essential tools which are not part of the Scandinavian tradition here. And the first is a connection to probability. And this is somewhat surprising, really, because everybody knows today that harmonic measure is the probability for a Brownian motion to hit a certain part of the boundary. And you would think that any student of potential theory or probability or both would realize it, but that's not the case. So the great master here is, of course, Norbert Wiener, and he was an expert in both probability and in potential theory, and worked on this extensively in the 1930s. But for some reason which I cannot really explain, it never occurred to him to have this interpretation of the harmonic measure. And that was left, I think, to Capitani to write a paper on that about 1940. But today, of course, we are this is a household word, really, that makes the connection to probability. And what is in particular important in probability, which is so useful in function theory, is the notion of a stopping time. Yeah, I give you some example of that very soon, but let me mention the other tool which were not used, and these are the singular integrals and the covering theorems. The heroic period didn't want to get involved in covering theory, which is somehow kind of dirty mathematics. You don't get the right constants, and everything is kind of combinatorial. And if you want to do beautiful mathematics, that doesn't really belong there. But it's an extremely useful tool when you want to understand kind of problems I've discussed. And I would just impress you here, if you don't know this before, by showing what you can obtain here. So, is a slide which relates to what I was saying. So on top here I describe the definition of harmonic measure, and the and the second part here is the description of Hausdorff measure, that you use coverings of the sets, and you have a measure function which is called H, and you look at the best coverings of the set using disks, say. So let me mention one of the highlights here in this theory, namely the results by Makarov, which was extremely impressive when one hears that the first time. So what you want to know is what is the connection between Hausdorff measure on the boundary of a curve. So you have a subset of a curve, and you want to know what is the connection between the Hausdorff measure of a subset there and its harmonic measure. And it turns out that, I mean, if you have a smooth curve, you would say that the length of the sets would be the decisive notion, and that is true, of course, for all smooth curves. But if you allow complicated curves, it is not. And what Michaelos did was that he found the correct Hausdorff size of a set so that you have a connection between the harmonic measure and the Hausdorff measure. And the correct way of measuring the size is the one given by H0 there. And I challenge anybody who doesn't know probability to find that function. I mean, there is no probability in the statement here. It is just a geometric statement about harmonic measure. But what is the time here? I put it 10 o'clock here. Sorry, have I crossed my time here? No? No? Okay. So the correct size of this function, of this set, is given by this measure function here. And of course, it comes from the law of the iterated logarithm in probability. And the reason is that the harmonic measure really behaves like probability, so just because of the connection to Brownian motion. So let me then just mention briefly how stopping time can enter here. And it also could be a little surprising. And that has to do with my work on the partial sum. So you want to estimate, say, a partial sum of the Fourier series, and you have a formula like the one I have written down there. And now you want to estimate this, you want to use coverings. And when you use coverings here to localize the integral which I had on top there, which disappeared. You want to localize that formula to a certain interval around x. And you want to use covering so you know where you should, so to say, how big you should make the localization. So what you do then is that you measure whatever you are doing in terms of local Fourier coefficients, the way I have written down. So when you start your covering, you have a certain size of this expression, and then you refine the covering until you have increased your measure by a certain amount, like a factor 2. And if you think about it, you see that this is precisely a stopping time argument. You see if your Fourier coefficients have gone up, and if they have gone up sufficiently, you stop and you start all over again and localize. And if they have not gone up, you keep on subdividing. And this, of course, is precisely the type of argument that one uses in singular function theory and in probability. So thank you very much. I hope I have given you an impression of the achievements of our colleagues here in Scandinavia.
Every time is the golden age of something, either by self-definition or popular acclaim. So what do you view this as the golden age of?
Oh, partnership.
Yeah, correct.
Is that good?
So what today, do you view it as the golden age of what you should invest or bet all your money on?
Well, I don't know how to answer that. I don't know really the question, but if I summarize it, it's a success of mathematics in Scandinavia, which was very much concentrated on this particular topic. And if the question concerns how this is going to continue, of course I cannot really say that. But it probably showed that it was the peak of the subject, and that we should in the future do something slightly different. Well, that's the question.
More questions? So I think we thank you, Abel Laureate, again.